Grade 1. He sees a lot of girls. Yo, this is your long one. Grade 1, man. Small world, small world.
So I want to announce first the plan for the next for the rest of the course. So today we are going to talk about Taylor polynomials, Taylor approximation. It's an approximation which is even better than linear and quadratic. And next we'll talk about estimating the error term linear approximation. That's next lecture, and it's not going to take us too long, so we'll probably be able next lecture to cover both error terms and derivatives of inverse trigonometric functions.
What?
Derivatives of inverse trigonometric functions. It turns out that, well, we'll talk about what it is, but it turns out that, well, for the next part of the course, for integration, it's important to know several more derivatives. Besides what we already know, several more. But that's, well, quite easy. It's just about several formulas.
Oh, yeah.
And this leaves us with one extra lecture on Thursday next week. And I plan to make a short review. If you have any questions, any suggestions, please bring them to me, send them by email, or well, communicate in any way. I will discuss those. If I don't get any questions, well, I will bring my own questions and discuss those. Okay, so let's talk about these Taylor polynomials. We already know two kinds of approximation: linear approximation and quadratic approximation. Let me go what those are. Formula for linear approximation. We approximate the value of a function at a point x by using the value at point nearby point x0. So here I want x to be not very far from x0. And then I have a correction term which is linear, which is just something times, well, x basically, times x minus some number. And this something is a slope, so we approximate our function basically by a line. Next, we got familiar with quadratic approximation. And this starts exactly like linear approximation. And that adds another term, another kind of correction term, which is now quadratic. It has a number, coefficient, f double prime of x0 over 2 times a quadratic term, x minus x0 squared. And this is now a parabola, a quadratic polynomial. And last time we talked about the fact that this quadratic polynomial, well, has the same value as the function at x0, has the same tangent line, and the same concavity. So first, two derivatives agree with the derivatives of f. Well, the initial question is, what happens if we try to add more correction terms? Well, it turns out that yes, it is a good idea to add more correction terms, to consider polynomials not up to degree 2, but up to any degree, up to degree n. Fix some number n, 7. And consider all polynomials up to degree 7, and among those choose the one which approximates my function in the best possible way at the point x0. Well, what do I mean? Well, we want the first 7 derivatives of our polynomial to coincide with the derivatives of the function n. So let me write down the answer, and we won't derive the answer. I'll just explain why this answer works. So Taylor polynomial order n around the point x0 is the following thing. First of all, it's a polynomial of degree n, and it looks like this. F of x0 plus f prime of x0 times x minus x0 plus f double prime of x0 times x minus x0 squared over 2 factorial plus f triple prime of x0 times x minus x0 cubed over 3 factorial. It goes on in this way until the nth degree, the nth derivative of f at point x0 times x minus x0 to the power n divided by n factorial. So before I discuss, well, what is this polynomial, why it is good, let me just recall what is n factorial. N factorial is just the product of numbers from 1 to n. So it's 1 times 2 times 3 all the way up to n. Let's say 3 factorial is 1 times 2 times 3, which is 6. Okay, and well, like this, these polynomials have the following property. The function f of x can be approximated using this Taylor polynomial for x which is close to the point x0. Well, so I wrote some polynomial, it has something, some number plus something times something with x, something with x squared, something with x cubed, all the way up to something with x to the power n. But you know there are many polynomials. Why did I choose this particular one? Why did I choose these strange coefficients? N's derivative over n factorial? Well, there is a reason. The reason is that this polynomial the nth Taylor polynomial satisfies such properties. Its value at the point x0, well, let's look. If you plug in x which is equal to x0, all these terms become 0. So it's exactly f of x0. The derivative at the point x0, well, look here. This will give me 0, this will give me f prime of x0, and all the rest will give me something times x minus x0 to some power. But when I plug in x equal to x0, all the rest will become 0. So the derivative is f prime of x0. And in fact it continues in this way. The second derivative is the same as the second derivative of the function, all the way up to nth derivative. So this polynomial at the point x0 behaves pretty much like the function itself. It has the same value, and the first n derivatives are also the same. Well, you might ask, maybe I have several polynomials with the same property. Why did I choose this one? But actually no, there is only one like this. So n, this is the only polynomial of degree n with this property. So if you want to approximate your function using the polynomial of small degree, so you decided you want to consider, say, only polynomials of degree 7, and that's it, no bigger powers of x. Well, then you try to think, is there some polynomial of degree 7 which has the same value of my function at some point x0, and the first 7 derivatives are also the same as the derivatives of the function? Well, the answer is yes, there is such polynomial, and this is the polynomial. There is only one. So let me give you some examples of this. First, some abstract examples, and then we'll do some concrete computations. So first one is, what is P naught of x? What is the Taylor polynomial of degree 0? Well, it means I want to stop at the zeroth power here. So not even go to x minus x naught to power 1. So that's just f of x naught. So the 0th degree Taylor polynomial is just a number. It's kind of horizontal line, a number. And it is a number which has a property, it is the actual value of the function at the point of c. So the next thing, first degree polynomial. Well, according to the formula, it's f of x naught plus f prime of x naught times x minus x naught. So you see that the first degree Taylor polynomial is exactly the linear approximation. Let's use the linear approximation. Well, second degree Taylor polynomial, you can guess what it will be. It's f of x naught plus f prime of x naught times x minus x naught plus f double prime of x naught times x minus x naught squared divided by 2 factorial. But what is 2 factorial? 2 factorial is just 2. It's 1 times 2. So it is the quadratic approximation. So you see that this formula for quadratic approximation and that formula for the Taylor polynomial of degree 2 is exactly the same thing. Well, as we would expect, that's the way we try to find the quadratic approximation. We want it to satisfy exactly the same property. Okay, but now we have a choice. We can choose any degree for this polynomial. We can continue to degree 3, 4, 5, whatever. So let's do this in some example. The example is like this. Find degree n Taylor polynomial of e to the power x around x naught, which is 0, and use it to compute e to these 5 correct digits. So we have the following task. First of all, write down what is the degree n Taylor polynomial of e to the power x, and then use it to approximate some number. In this case, the number is just e. So we'll pretend that we don't know exactly what is e, or at least we don't know what are the first 5 digits of e, and we'll try to find it. So we have this problem, we want to find the degree n Taylor polynomial. So we look at this formula, we see that we know here everything except, well, these coefficients. f of x naught, f prime of x naught, and so on. So we want to find the value of the first n derivatives of the function at the point x naught, in this case 0. So let's solve it. My function is e to the power x. Its derivative is e to the power x. Second derivative is, well, you can guess how it continues. We'll repeat. I mean, the derivative of e to the power x is e to the power x, no matter how many times you repeat this process. So all the way up to n's derivative, you'll still get e to the power x. Well, that's good. Of course, we don't want the actual derivative. We just want the derivative at the point x naught. So let's compute the derivatives at the point x naught. F of x naught is e to the power 0, which is 1. F prime of x naught is e to the power 0, which is 1. And this goes all the way up to its derivative, which is also 1 at the point 0. So now we have all the coefficients, and we can write down the answer. I want to have the formula for Taylor polynomial at the end of the lecture, but I don't want to use this part of the board, so maybe I'll copy it here. Against degree Taylor polynomial is f of x naught plus prime of x naught x naught double prime of x naught factorial. Hence, derivative of x naught is x naught n over n. Sorry for this break. I just wanted to have this formula. Okay, so back to the actual problem. We computed the coefficients, all the derivatives. Now we can write down the answer. In n of x, the nth degree Taylor polynomial is, well, f of x naught, which is 1, plus the derivative times x minus x naught, which is x minus 0, plus second derivative times x minus x naught squared divided by 2 factorial, third derivative times x minus x naught cubed over 3 factorial, and it continues all the way up to nth derivative, still 1, times x minus x naught to the power n divided by n factorial. So just plug in these coefficients into that formula. And now I can rewrite this in simpler way. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way up to x to the power n over n factorial. So this polynomial, once again, it is the only polynomial of degree up to n with the property that its value at the point 0 is 1, and the value of all of its derivatives up to order n at the point 0 is also 1. The value of this polynomial is the same as e to the power 0, and the value of all its derivatives up to degree n is the same as the value of derivatives of e to the power x at the point 0. Okay, so we have this polynomial. Well, it is some polynomial. Is it useful actually for approximation of stuff? For example, is it useful for trying to know what is e? To be honest, to this point in the course, we never actually talked about what is the value of e. We introduced it, if you recall, we introduced it as some base, or some number, such that for the graph of this number to the power x, so it's some number e such that the graph of e to the power x has a tangent with slope 1 at the point 0. That was the official definition of what was e. And if you recall, well, we had an argument why it's a little bit bigger than 2 and a little bit smaller than 3. And that's it. We didn't know anything more than this. And if you wanted to know what is actually e, well, we had to ask a calculator or a textbook, but basically you couldn't argue. I mean, you couldn't convince somebody else that your textbook was correct or your calculator was correct. Well, now we have a way to do this. What is e? Well, e is e to the power 1. Well, it looks like 1 is quite far from the point 0. So maybe this Taylor polynomial will not be very good. Well, but let's see. We have here some freedom. We can choose the order of this polynomial to be as large as we want. So let's see. The approximations are as follows. If I want degree 0 approximation, what is it? I just take one term, and that's 1. Well, that's not that good an approximation. E is, well, it is approximately 1, of course, but it is also quite far from being 1. So this approximation is the following approximation. E to the power 1 is approximately e to the power 0. Well, yes, it is, and it is. Next approximation is a little bit better. It's 1 plus 1. And that's degree 1 approximation. Well, we got it a little bit better. The linear approximation to e is, well, 2. Okay, still doesn't look very promising, but let's continue. E is approximately 1 plus 1 plus 1 over 2 factorial. So it's 1 plus 1 plus 1 half, 2.5. That's the quadratic approximation. That's the best we could do last lecture. So last lecture we could have concluded that E is about 2.5. Okay. Now we can do better. We can continue to cubic approximation all the way up to degree 3. 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. So it's 1 plus 1 plus 1 half plus 1 over 6. So it's 2 and 2/3. So 2.6666. And that's degree 3 approximation. Okay, we are getting a little bit closer, but still we can try to continue. Degree 4 approximation. 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. And it's 1 plus 1 plus 1 half plus 1 over 6 plus 1 over 24. 4 factorial is 1 times 2 times 3 times 4 is 24. Well, I hope that I computed it at home. Yes, I did. So it turns out to be 2.7083. And that's degree 4. Okay, before I continue with the calculations, let me ask you the following question. How will I know that I computed enough? I mean, I want 5 correct digits for the number e, so how will I know when to stop? Maybe I already had to stop here. Well, no, because at this step I had to make a correction to this digit. Well, I also didn't want to stop here because the next step corrected this digit once again. So when will I know that I'm ready to stop?
So you remember stops here.
Yes, exactly. So keep track of the first 5 digits, and when on the next step they stop changing, well, I know that I'm either done or almost done. but probably done. Okay. So let's continue. Here I see that the third digit changed once again, so I'm probably not done here. Degree 5. E is about 1 plus 1 plus 1 half, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. So it's 1 plus 1 plus 1 half plus 1 over 6, 1 over 24, and 1 over 24 times 5 is 120. So it's 2.7166. So I see that the first digit didn't change, but the second one did. So still I'm not done. Degree 6. Well, it's approximately I continue this process up to 6 factorial now. Half, 1 over 6, 1 over 24, 1 over 120, and 1 over 720. And this turns out to be 2.7180.
It's not even close enough.
Sorry?
It's not close enough.
So this number, well, what happened? The first 3 digits now are the same, but the next one seems to grow. Well, we continue next. So, degree 7 approximation would have e to the power 1 being approximately 1 plus 1, 1 over 2 factorial, up to 1 over 7 factorial. So let me not go into extending this. Let me write down the answer, 2.7182. So still the first 4 digits didn't change. And for degree 8 we have 7182 and so on. So even though the point 1 was, well, quite far from the point 0, where we knew the value of e to the power 0, and the first couple of approximations were really, really bad, I mean, the linear is about 2, well, quite ridiculous. Next one was better, the quadratic one, but still pretty far. Well, the 6th one already had 3 correct digits, 7th one had 4, 8th one had 5. And if you think about it, well, in the 7th approximation, the next term that we added to the previous one was 1 over 7 factorial. 1 over 7 factorial is 5,000 something, 5,040 something. Oh, so anyway, it's about 5,000. So the next correction term that we added was, well, 1 over 5,000, really small. The next one was even smaller. It's 1 over 40,000. So it was even smaller. And the next ones will be, well, 40,000 times 9 times 9, 40,000 times 9 and times 10. So they will become smaller and smaller and smaller. So we are pretty sure that these digits are actually correct. Because once again, all the other terms will be much, much smaller. They will alter only those digits far away. So, okay, so maybe first questions about this computation. Well, then let me tell you a short story which is kind of not part of the material, but still. we have such a formula. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. So I rewrote this approximate formula, but now I put inequality sign and dot dot dot, which means I never stop. So if you take this Taylor polynomial and you allow yourself to add all the terms, not stop at degree 8, not stop at degree 9, just continue adding infinitely many terms, then first of all, it makes sense. The terms eventually become very small and adding them doesn't change the result by too much, whatever x is. Even if x initially is, I don't know, 10, you will get something like, the first couple of terms will look like they are growing. 1 plus 10 plus 50 plus 166 and something like this. It looks like the first couple are growing. Starting from term, I don't know, 10, they will become pretty small. They will become kind of corrections like this, 0.1, 0.005. So eventually, for any x, this process will converge. You will get results which start, the first 3 digits will never change after step number 5. The first 7 digits will not change after step number 12. So for any x, it's possible to compute this whole infinite sum. And second thing, your calculator actually doesn't know any other way of computing e to some power besides this one. So the calculator doesn't actually know what is e to the power 5.31. It can't take e from its memory. I mean, yes, it does remember what is e. But it can't take it and multiply it by itself 5.23 times. It's meaningless. You can't multiply a number by itself 5.23 times. What it can do, however, is take any number and multiply it by itself how many times you want. It's really good at multiplication, it's really good at division, it's really good at, well, addition. So it can compute all such things. What it actually does is, well, exactly like this. It keeps in its memory the result of adding first several terms in this formula. It keeps 10 digits of precision, and it shows to you only 8, of course. So when this process stabilizes and the 10th digit stops changing, well, it outputs your answer. And calculators are pretty fast, and they do this process very fast. So this way, even though you think that you are computing e to the power x, what you're actually computing is the value of this polynomial. Well, not polynomial, series, it never stops. Well, but the result is exactly the same. Okay, so we'll talk about this much more in 105. So we'll talk how calculator computes sine of x, cosine of x, and so on and so on. Turns out it's exactly the same process. But for now, let's talk about. So for now, let's talk more about this Taylor polynomial. This first example was, well, kind of toy example. It was very easy to compute the derivatives. Let's use something less obvious. So example, find the Taylor polynomial of square root of x around x naught equal to 4. A polynomial of order 3 and use it to approximate square root of 5. So such a problem is more typical. I mean, the function e to the power x is maybe the simplest function to differentiate, but most functions are not that easy to differentiate. So let's discuss this problem. Well, basically it's the same kind of problem. Here's the formula, here's what you would want to compute, actually do the computation. So the formula for the Taylor polynomial is like this. We want the Taylor polynomial of order 3. It means we will want to stop at the third derivative right here. So let's compute the three derivatives. F of x is square root of x. F prime of x is, well, this is x to power 1/2, so it's 1/2 x to minus 1/2. Second derivative, 1/2 times minus 1/2 is minus 1/4 x to minus 3/2. And third derivative is minus 1/4 times minus 3/2, so it's 3/8 x to minus 5/2. So now we don't really see a pattern to this. I mean, yes, something happens, we don't know what these coefficients are going to be on the fourth step, on the fifth step, but that's also not part of the question. We know that we're only interested in Taylor polynomial of degree 3. So we are only interested in first three derivatives. And we are interested in these derivatives at the point x0, which is 4. So f of x0 is square root of 4, it's 2. F prime of x0 is 1/2 times 4 to negative 1/2, so it's 1/2. So it's 1/4. Second derivative is minus 1/4 times 4 to negative 3/2, so it's 1/2 to the power 3. So it's minus 1/4 times 8, 32. And f triple prime at x0 4 is 3/8 times 4 to negative 5/2, so it's 1/2 to the power 5. So it's 3/8 times 32, 256. Okay. So we found the first three derivatives at the point x0. We have these coefficients. The rest is just write down the polynomial. So the polynomial of degree 3 of x is, well, f of x0, which is 2, plus the derivative times x minus x0. Remember that x0 is 4. Plus the second derivative, which is negative 1/32, times x minus 4 squared over 2 factorial. Plus the third derivative, which is 3/256, times x minus 4 cubed divided by 3 factorial. Well, let's simplify it just a little bit. What you definitely do not want to do is, you do not want to open the brackets here. This x minus 4 to some power is quite essential. You want to leave it as x minus 4 to some power, because you are going to use this approximation for point x, which is close to the point 4. So this difference will be small. So you do want to leave the brackets here. But you do want to simplify the coefficients as well, because, well, it's easier to compute with simple numbers. So minus 1/64 is x minus 4 squared plus 3 divided by 256 divided by 2 and divided by 3. will be cancelled out, so we get 1 over 512 x minus 4. So that would be the answer for the degree 3 Taylor polynomial around the point 4. It is written in terms of powers of x minus 4. And next we want to use it to find the approximation to square root of pi. Well, that's very simple. We just plug in x equal to 5. Because you want to find the square root of x, which is 5. So it is 2 plus 1 over 4 times 1 plus, minus 1 over 64 times 1 square and plus 1 over 512 times 1 cube. So 5 minus 4 is 1. So this thing is just 1. So it is 2 plus 1/4 minus 1 over 64 plus 1 over 512. And well, if I were on some kind of exam, I would leave it like this because I don't want to actually compute this without a calculator, and you're usually not allowed to use a calculator on an exam. But since I'm not on an exam, I will compute it. So it is 2.2363. So the question was, suppose that the question is find the 18th degree Taylor polynomial. Well, if the function is complicated like this square root and there is no obvious pattern in the derivatives, you will not be asked on an exam to compute the 18th degree Taylor polynomial. For some functions, we'll see an example just in 1 minute. It is possible to find a pattern in the derivatives, and then it's quite easy. Okay, in this answer, in fact, will return 4 digits are correct. And you see that the correction terms actually do seem to get smaller and smaller. We have this one is already kind of 0.0002. So the correction terms get smaller and smaller. It's reasonable that actually something of this kind should be right. Okay. So, any questions about this? Well, I would say simple and standard kind of questions. Here is the formula, compute the Taylor polynomial. Let's then discuss a problem which is slightly more complicated. So now it's not an example, it's a problem. First part, find the coefficient of x to the power 2013 in the Taylor polynomial. Sine of x around 0 of degree of order and part B, same for order 100. first, what is the question? The question is, you are given a function, and the function is sine of x. The question is about the Taylor polynomial of this function around the point 0, and the order of this polynomial is 10 thousandths. And what the question is asking is, what is the coefficient of x to the power 2013? Well, let's imagine for a second how this polynomial itself will look like. We have this function, f of x is sine of x, and the polynomial of degree 10 thousandths is some function like this. It's f at the point 0 plus derivative times x minus 0, which is x, plus second derivative at 0 times x squared over 2 factorial. And we should continue up to the 10 thousandths derivative at the point 0 multiplied by x to the power 10 thousandths over 10 thousandths factorial. So that's how the polynomial looks like. What the question is asking is, well, somewhere hidden here, probably somewhere in this space of the 3 dots, some term is x to the power 2013. And the question is, what will be the coefficient of this x to the power 2013? Well, first of all, in a way it's obvious what it is. It's the 2013 derivative of f at the point 0 divided by 2013 factorial. Okay, so it is a step in the right direction, of course. So the coefficient of x to the power 2013 is the 2013 derivative of f at the point 0 divided by 2013 factorial. So if you imagine what stands here near x to the power 2013, it's this number times x to the power 2013. Well, what we are still missing is this part. What is the 2013's derivative of our function? So what is 2013's derivative of sine at the point 0? Well, I can try to stare at it and think for a second, but well, it doesn't help much. So I'll start, well, without much hope for success. I'll compute the first derivative. The first derivative of sine is cosine. Well, second derivative of sine is minus sine. It's derivative of cosine. Third derivative of sine is minus cosine of x. Fourth derivative of sine is minus derivative of cosine is minus sine, so it's plus sine.
So it's every 4.
Fifth derivative of sine is cosine. Well, if I had really lots of time and patience, I would write down another 2009 lines like this, but I won't. The reason is because I can look at this and see some pattern. What pattern do I see here?
Every 4.
It repeats every 4 steps. So the fourth derivative of sine gets me back to sine once again. Once I apply extra 4 derivatives, well, I'll get back to sine once again. Apply another 4 differentiations, back to sine. So the 8th derivative of sine is once again sine. I mean, it's the 4th derivative of the 4th derivative. The 12th derivative of sine is sine. This continues all the way up to 2012 derivative of sine, because 2012 is divisible by 4. And then I know that the 2013 derivative of sine is cosine. And now I'm ready to answer the original question. So answer, it's 2013 derivative, which is cosine, at the point 0, divided by 2013 factorial. Or in other words, it's 1 over 2013 factorial. So basically this question had two main ingredients. First ingredient was remembering the Taylor formula. Imagining the Taylor polynomial, how it looks like, that it actually has powers of x and some coefficients, and that these coefficients are given exactly by such formula. X derivative divided by n factorial. It was up to here. Next part was about computation of 2013 derivative of sine, which, well, is a bit of a trick. We had to find the pattern in these derivatives, and the pattern was quite easy. Of course, derivative turned out to be the same as the function itself, and this helped us. For kind of random function, you wouldn't expect to have a pattern. For square root of x, there is a pattern, but it is complicated. For even more complicated functions, like tangent, there is more or less no pattern. Okay, so any questions about this type of problem? Yeah.
Why did you choose an order of 10,000 if the x is 2,000?
Okay, so let's talk about this in part B. Because in part, so it's true that if I chose, say, 100,000 here or 1 million, it wouldn't make any difference. But let's look what if the order is just 100. Let's talk about part B. So now I want to talk about the coefficient of x to the power 2013 in the Taylor polynomial of sine of x around 0 of order 100. So maybe somebody has an answer.
What?
So I'm talking about part B now, and the question is, what is the coefficient of x to the power 2013 in the Taylor polynomial of sine of x around 0 of order 100? Okay.
Sine 0.
Sine 0. Actually, no. In a way, yes, but not because of the reason that you think it is.
Oh.
Well, it's much simpler than this. In fact, it's more or less obvious. It is 0. The reason is because the polynomial of degree 100 has the following terms. It has something, some number plus a number times x plus a number times x squared, all the way up to a number times x to the power 100. What is the coefficient of x to the power 2013? Well, there is no x to the power 2013. It just doesn't appear in this polynomial. We stopped at step number 100. We never continued all the way to 2013. So x to the power 2013, it should have appeared well, somewhere here. It just doesn't appear. It appears with coefficient 0. So the coefficient of x to the power 2013 is 0. So this part was, well, maybe a little bit more tricky, but much simpler than the first part. We didn't have to make any computation. So in a polynomial of degree 100, there is no term x to the power 2013. That's the answer.
Would it not then be does not exist? Why 0?
I mean, if you write 0 times x to the power 2013, it's the same as not writing it at all. So, I mean, you can write this, I mean, you can say that this is plus 0 times x to the power 2013 English. Any term which does not appear in the formula, you can say that it appears with coefficient 0. So that's, I would say that's a convention. Okay, so we have just enough time to consider the problem which is, well, a little bit more complicated than this and, well, a little bit more interesting. So it will be an example of the following type. Suppose y of x is defined implicitly by x plus y squared x plus 2y squared plus 1 over x is equal to 0, and y of minus 1 is equal to 1. Find the degree 2 Taylor polynomial of y of x around minus 1 and use it to sketch y of x for x which is close to minus 1. So this is a problem of entirely different kind. Here we want to use our knowledge about Taylor polynomials to sketch a function. And not just a function which is defined by an implicit equation. It's just defined by satisfying some equation. I mean, true in this case, the equation is simple enough, it allows us to isolate y as a function of x, but we will not do this. I mean, it's just, I chose this equation to be simple, all the computations in class to be simple, but in general, it will work for any kind of equation. So let's look at what sort of a problem this is. We have some relation between x and y. It defines some curve in the plane. For some x, there might be several y's, so it might look, I don't know how it looks exactly, some kind of curve. And if you just try to plug in x is equal to minus 1 and y equal to 1, we see that this point is on this curve. So if x is minus 1 and y is 1, we see that such a point is on the curve. And the question is, well, around this point, my function y is in fact a function of x. It's not just some weird equation, dependence, it is a function of x. I mean, once I know that the value at -1 is this one and not the other one, I have, well, part of this thing which defines a natural function. For every x, just one value of y. And the question is, no, I have a function, it must have some Taylor polynomial. What is this Taylor polynomial? Okay, so let's think what we should do. In the end, we want to find the second degree Taylor polynomial. What we should do to actually find. Well, maybe let me copy this formula. The second degree Taylor polynomial will be y at the point -1 plus the first derivative of y at -1 times x minus the point, which is -1, plus y double prime of -1 times x minus the point squared divided by 2 factorial. So, for any function y of x, the Taylor polynomial of degree 2 around the point -1 looks like this. Well, but of course I don't know several things in this polynomial. What things I don't know? Well, this thing, and that thing. There should be some numbers, I just don't know what these numbers are. Okay, let's find out. First of all, this number, y of -1. What is this number? 1, of course 1. It's just given to us that y of -1 is equal to 1. We chose y to satisfy at the point -1, it is equal to 1. Okay, next part. What is y prime at the point -1? Well, this is less obvious. We can't just stare at this equation and say what it is, we have to work. So what should we do to find the derivative at -1? Differentiate this implicitly. Take this equation and differentiate to find some relation between x, y, and y prime. So differentiate implicitly. So it will be 1 plus 2 times 2y times y prime. And derivative of 1 over x is -1 over x squared. So I get such an equation. This holds at any point x comma y. In particular, well, I want to find y prime at point -1. So at when x is -1, y is 1, and then I have 1 plus 2 times 2 times y, which is 1, times y prime at -1, minus 1 over x squared minus 1 squared is equal to 0. So I have 1 plus 4y prime minus 1. So the total is just 4y prime point -1 is equal to 0. And I find that y prime at -1 is equal to 0. Okay, so I already see that my sketch over here wasn't correct. The tangent line at this point, well, is not like this, it is horizontal. The slope will be equal to 0. So I have to modify such a sketch and somehow make it horizontal. Anyway, I further want to find the second derivative at the point -1. Well, same idea. I want to find a relation between the second derivative and x and y. Well, I take this equation, which involves the first derivative, and differentiate it once again. So differentiate. 1 plus 4y by prime minus 1 over x squared is equal to 0. And what we get is, so here I will apply the product rule. 4 times derivative of y times y prime plus 4y times derivative of y prime, which is y double prime, minus derivative of 1 over x squared. So it's x to minus 2, derivative is minus 2 divided by x cubed. So I get such an equation. I can plug in my point. By the way, as usual, it is important to differentiate the correct equation, the equation before we plugged in the point. Once we plugged in the point, we destroyed all the dependency. We just have the equation only at one point. We don't want this. We want the actual dependency. So I want to differentiate this equation, not say this one. Okay, so from differentiating this, I found this, and now add x, which is minus 1, y is equal to 1, y prime, I will need what is y prime, but I already know what it is, it's 0. And then I have 4 times 0 squared plus 4 times 1 times y double prime point minus 1 plus 2 divided by x cubed, which is minus 1 cubed, is equal to 0. So 4 y double prime minus 1 plus minus 2 is equal to 0. And y double prime minus 1 is 1/2. So in this case, well, we had to compute this first and second derivative. Well, it wasn't that easy. We had to differentiate implicitly, but well, we succeeded. We found the first derivative, the second derivative. Let's write down the answer. The second degree Taylor polynomial u2 of x is the value of y at the point 0, which is at the point minus 1, which is 1, plus the first derivative times x minus minus 1. So I look here, x minus minus 1 is x plus 1, plus the second derivative, which we found here, 1/2, times x plus 1 squared over 2 factorial. Now let's simplify it a little bit. It's 1 plus 1/4 x plus 1 squared. So that's our answer. P2 of x is 1 plus 1/4 of x plus 1 squared. Well, that's just the algebraic part of the question. How to find the second degree Taylor polynomial? We'll find the two derivatives, plug them in. To find the two derivatives, we'll differentiate implicitly 2 times and plug in the numbers. Now, kind of the heart of the question. Why did we do this? Well, we did this to try to sketch this function around the point minus 1. Well, let's try.
Such a possible.
Sketch.
Actually, that's correct for this one.
Okay, so first of all, what do we actually know? So, what data can I use to sketch my function around the point -1? Okay, so first of all, the function at the point -1 is 1. So I have this. I also know that the tangent line will be horizontal. And somehow I also use, well, we also find the second derivative. How can we use the second derivative? Okay, it's concave up. It will be something like this, but how much is it concave up? Is it something like this or something like this? What should I do? Well, we actually do know, because we found the quadratic approximation. And quadratic approximation, well, is an approximation of the function. So my function, when x is close to -1, is actually quite close to this thing. Whatever x, my function, well, if it is close to -1, my function will look exactly like, well, not exactly, but close to this parabola. So what I should draw is just draw the graph of that parabola. At point -1, it is indeed 1. Then it has a minimum at this point, because it's 1 plus something that vanishes at this point, and then square. And next, well, to know how fast it grows, let me just plug in some points. Say at 0. 1 plus, at 0 I have just 1/4. So here I have 2, 2 and 1.5, 1.25. At the point 0, my parabola is like this. And the same at point -2. So my parabola is actually like this. Well, about this parabola, well, for the parabola I can draw the accurate graph. I do know precisely what is my function. For the function itself, it's not the accurate graph, it's only an approximation. But when x is close to -1, it should be a good approximation. So I won't continue this graph maybe to 10 or to -10, it would be more or less meaningless. But at least around the point -1, I do know that this represents a quite precise graph. It's not something like this, it's not something like this, not something like this, it's exactly like this. If I wanted to verify how precise my graph is, well, I would do something like this. I would compute the third approximation, sketch the third approximation, see how much it deviates from the second one, and on the region where it doesn't deviate too much, I will know that my approximation was good. And so on. So if you actually want to sketch the whole curve, it makes sense to do the following procedure. Choose a point, find the Taylor polynomial, sketch the Taylor polynomial. Well, at the nearby point, find another point on my graph, find the Taylor polynomial, sketch the Taylor polynomial, and so on. And once again, it sounds like a complicated algorithm and lots of calculations, but if you think about it, well, it is a pretty good algorithm for a computer to do this. And the computer, algebraic system like Mathematica or Maple or MATLAB actually follows some variation of such an algorithm. It actually uses maybe splines and degree 3 Taylor polynomials to sketch such curves. So this simple stuff that we're discussing here is actually the complicated stuff which lies behind calculators, computers. So it is actually useful. Okay, so maybe questions about this part. So I have yeah.
So how do you find a more accurate sketch of the graph?
So once again, here I didn't find it. So my question was just sketch a graph as accurate as you can, and well, I did. If I actually wanted to find out how accurate it is, I would try to find this third-degree polynomial, sketch it. It will look somewhat like this. Then I know my graph is pretty good here, and it's quite open. So see you next time.